I'm going to draw our free body diagram. I'm going to draw it big. Okay. So this is where our geometric datum is. So this is for point A, right? So the distance from here to here is x now. Okay. Now, if we look at our equivalent load, we have our equivalent load coming down here. And this equivalent load is equal to 50 times 10 to the power 3 multiplied by what? X. Okay. And because of the fact that this is an evenly distributed load, the distance from here to here becomes x. Wait, let me put it elsewhere. It looks a bit messy. So this distance over here, right, becomes x divided by 2 because it's evenly distributed load. Okay. And I can recap with you to why. Okay. So let's say now we have a beam. You guys have seen this before. Only thing is it's a function of x. Okay. So if we have a load or we have a beam, the beam is simply supported. And then I have an evenly distributed load. Right. I have an evenly distributed load. And this evenly distributed load omega is good 10 kilonewton per meter. And the distance from here to here is 4 meters. Right? Right? So now if I want to find the equivalent load of a distance 4 meters, so we know that there's a reaction over here. So I'm going to call this point A, point B. So we know that there's a reaction at AY, and there's a reaction at BY. And we know the equivalent load will be equal to 10 times 10 to the power 3, right? Because it's in kilonewton, and we have to multiply by 4. So this is 40 times 10 to the power 3 Newton. Where is this load acting to is what we do. Is we do 4 divided by what? Divided by 2. So this is 2 meters, right? Now, coming back to this now. What if now I call this X, right? So what we have over here is 10 times 10 to the power 3 X, right? Because this distance is what? This distance is X, right? And then the equivalent load over here, this equivalent load will be X divided by 2. So that's where what we have done is exactly the same. Okay. Now let's say now, okay, for example, now if we have a triangle load, okay, because we can have any sort of distribution. If we have a triangle load, okay, so the same beam, right? We can see the same beam, and then we have point A, and then we have point B, right? Now triangle load is a bit not confusing, but let's look at the entire triangle load. So now if we have a triangle load now. Okay. And this triangle load we have over here is 10 omega is your 10 kilonewton per meter. And you have a distance from here to here. This is also, I call it 4 meters. So now the equivalent load now, right, in terms of magnitude, so this is equal to AY. This is equal to BY. And we know the equivalent load will act somewhere around, not somewhere, we know a very specific distance, right? So let's look at the load. So it's a triangle, so it's half base times height, right? So the equivalent load over here is equal to 20 times 10 to the power 3 Newton. Okay. And the distance from here to here is equal to 4/3 meters. Okay. So why? Because we have a distance over here as 4. Okay. Now I'll come back to the triangle load later when we are dealing with a function. Okay. I don't want to cram too much in your mind now. Okay. So now this is straightforward. Now let's go back to our free body diagram. This is straightforward to draw. Okay. So this everyone can draw this. Okay. So this is straightforward to draw. So now the thing is this. The shear force now is still in this direction. V as a function of x, and then moment as a function of x. And you guys will say, Eugene, there's something wrong over here. The whole block will slide down. Yes or no? Right? We all thought, or when I was young, I thought that V as a function of x has to be acting upwards. Okay, moment wise, okay, I can accept moment. Okay, so i.e. this is not in a static equilibrium, but why is this direction correct? Okay, so I'm going to explain the theory. Okay, so the theory that I'm going to explain is known as positive shear and positive bending moment notation. Okay, I'm going to explain what do we mean by positive shear and positive bending moment notation. So now, if we are going to analyze the structure, we're going to analyze structure from left to right. Okay, and the structure from left to right. So the structure of analysis in this direction, right? Left to right. So based on positive shear and positive moment notation, right? And one thing I want to elaborate, okay, the geometric datum is always on the left-hand side. Okay, so this is our geometric datum. Is again, I repeat, the geometric datum is on the left-hand side, because later on, when we analyze the structure from left to right, the geometric datum did not move and will not move. Okay, so this is x. So when you analyze the structure from left to right, the geometric datum, the shear force V as a function of x is coming down, and the moment is going anti-clockwise. Okay, so where is the point of interest is at x. Okay, at where x is, this is the point of interest. Okay, that is where you want to analyze. Okay, not the datum, but at when xn, when the distance x stop, that is where your point of interest is. Very important. Okay, listen to what I say. If you cannot remember, watch this video again. There's a lot of content in here. Now, what if then the next one, I want you to compare. Okay? We're going to analyze structure from right to left now. Okay, right? So you're going to analyze in the other direction. Later on, I will show you an example. Then it's more clear for me. So the geometric datum is still on the left-hand side. Did not change. But now it's of interest is the other side of the beam. Okay. So your geometry did not change, we want to find a distance x over here, right? And because we reach the other end of the beam, let's say if the entire length of the beam from here to here is L, the distance from here to here is L minus X. Okay, it's L minus X. It's not X minus L, yeah? Why is it L minus X? Because this number over here, mathematically, it has to be positive. It cannot be a negative number. It has to be a positive number. Because what is a negative number in a structure? When your datum is a negative number over here means you're dealing towards the left-hand side. Yes or no? So it always have to be what? A positive number. So when you analyze your structure from right to left, your shear force is now going upwards as a function of x, and your bending moment will be going clockwise. Okay. Again, you ask me, Eugene, at this case, where is the point of interest? The point of interest is over here. Okay, so this is the point of interest. Okay. Now, question for you guys. Why is the geometric datum always on the left-hand side? Anyone? Again, I ask, why the geometric datum has to be on the left-hand side? Why it cannot be on the right-hand side? Anyone? And the reason is not difficult. Okay. So at the end of the day, okay, I'm going to copy the diagram. Okay, now I think it will make a very good explanation for you guys. Okay. So if you see the structure that I've drawn now down here, or paste down here, why is the geometric datum, right? We're always very curious. Eugene, why the geometric datum never move? At the end of the day, what do we want to achieve? Okay, we always have to ask ourselves at the end of the day, what we want to achieve. We like to draw, right? We like to draw the what? Shear force and bending moment equation. Okay, or diagram, right? This is what we want to achieve. So in that context, if we were to construct any shear force or bending moment diagram, so we start with our shear force diagram, right? We start. So this is our V, and this is our X, right? It can be V, it can be also your M, either way. When you construct the diagram, 0 is always on which side of the diagram of the structure? It's always on the what? Left-hand side. So over here, right, when we construct our shear force and bending moment diagram, the origin is fixed, i.e., at point distance x equals 0 is always on your what? Left-hand side. That's why your geometric datum will not and shall not move. Okay, so on this context, either you analyze your structure from left to right or right to left, right? Geometric datum did not move at all. Geometric datum is fixed. Okay, so the geometric datum, so whether you analyze your structure from left to right or right to left, the geometric datum is fixed. Okay, so that is why when we drew the analysis on the free body diagram from A to B, 0x to 0.8, right? That is why our geometric datum did not move. And this is why, whoa, something moved down here is so weird. Okay. So that is why over here, go on. This is our